Good day, gang. Welcome to Section 2, Natural Gas Overview. Learning objectives for Section 2 are to be able to explain the formation and composition of natural gas, explain the difference between conventional and unconventional natural gas, list and describe the 6 different types of unconventional gas, and describe some of the trends of natural gas with regards to production and consumption. Key terms for Section 2 are methane, TRAPS, conventional and unconventional gas, differing from conventional and unconventional oil, which we talked about last section, associated gas, deep, tight, and shale gas, coal bed methane, geopressurized zones, methane hydrate, liquefied natural gas, liquefied petroleum gas, propane, ethane, butane, mercaptans, and inerts. Now, folks, these terms are going to be vital for you for the remainder of the term. Same with last section as well. They're going to be used interchangeably quite a bit, so I need you to understand them very, very well. Like I said, they're going to be used especially when we talk about drilling later on, when we get into production and trading. So the understanding that natural gas in a reservoir is made up of methane, propane, ethane, and butane, and the inerts. There's also helium and sulfur in there as well. When you take out the methane, okay, which they also refer to as natural gas, but you had to be able to associate the difference. When you take out the methane, it then is refrigerated, is turned into liquefied natural gas. Then when propane, ethane, and butane are taken out of natural gas and they are refrigerated, they are referred to as liquefied petroleum gas. So this is all very, very important and fundamental for the rest of the term. So please take the time to truly understand and how this all works. Thank you. Okay, let's get started here. Natural gas. So the first thing that's going to screw you up is the interchangeable usage of the word natural gas and methane in the books and literature. So you really have to understand what they're talking about in context. So when I talk about natural gas, especially here in the first part of these couple of chapters, I want you to think of natural gas as natural gas in the reservoir. So it's going to be some part of it is going to be methane, and there's going to be nitrogen, ethane, CO2, water, butane, propane, mercaptans, and other heavier hydrocarbons. So I don't want you to think of just pure methane, okay? When we talk about getting to the liquefied natural gas, then we'll actually specify methane, okay? So in the slides and in the book, the two terms, methane and natural gas, are sometimes used interchangeably. But what I want you to start thinking of originally is natural gas as all of it together in the reservoir, unfiltered in that stage. So like I mentioned before, at this stage I want you to think of natural gas as natural gas in the reservoir. So at this stage, methane makes up the main component of the natural gas, anywhere from 80 to 97%. And when later on, when methane is extracted and it's pure methane, it's either going to be shipped in pipeline by a gas form or refrigerated and turned into LNG. All right. The next stage is propane and butane. Isobutane is in there as well, and ethane, and they are referred to as petroleum gases. And when they're removed later on, they'll be referred to as liquefied petroleum gases. Pentane, hexane, and heptanes are referred to as condensates. And then, of course, the inerts, stuff that doesn't burn, carbon dioxide, nitrogen, and water. When I was second mate down in Brunei, trained to be a chief officer, I just assumed that all the material from the reservoir was being sucked out, refrigerated, and turned into liquefied natural gas and loaded on my ship. And obviously I couldn't have been more wrong. So the compositional makeup of natural gas in the reservoir changes quite a bit depending on where you are in the world. It even changes quite a bit in between the reservoir itself. You might have a pocket over here, a pocket over there, and a pocket over there, all in the same field, but even then the compositional makeup will be different. So I want you to be aware of that. That's what I want to get across in this particular graph. So if you were here in site number 1, your compositional makeup of methane is 79%, and over here, depending on where you are in the world, it could be 95. Your petroleum gases over here is quite high, 16 and 14, but over here it's 0.1 and 0, next to nothing. Same over here, your inerts, 4%, almost 5%, and then over here, 0.1 and 0.3, next to nothing. So in your reservoir, the compositional makeup of methane, ethane, propanes, your inerts, condensates, can vary quite a bit, and I need you to know that. Next, we're going to discuss conventional and unconventional gases. The difference between the two really only depends on the porosity and permeability of the rock and the extraction method techniques. Conventional gas is how you would normally expect gas to be extracted. You have a reservoir, a rig drills down and installs a well, and because of the porosity and permeability of the reservoir rock, gas flows to the surface under natural pressure from the reservoir. This is called primary extraction. Over time, the well will lose pressure as the gas is extracted, and then secondary techniques are used where pressure is maintained in the reservoir by injecting water and other gases into it. So I want you to understand that conventional gas is associated with good porosity and permeability, which allows flow under natural pressure of the well. So unconventional gas differs because of the porosity and permeability of the formations that the gas is trapped in. The formations are usually super dense, with low porosity and permeability, and the techniques used to untrap the gas from these formations are what makes them unconventional. Also, I want to be clear, the gas itself, no matter what method used to get it to the surface, either conventional or unconventional, the gas is still the same compositional makeup, containing methane, petroleum gases, condensates, and inerts. So the main types of unconventional gases that we're going to talk about here are shale gas, tight gas, and coal bed methane. So in the past couple of slides, I've been throwing around the two terms porosity and permeability. So before I can explain them, I want to ensure that we're all clear that there's no big vast swimming pools of liquid or gas in a reservoir. The oil and gas travels within small pores between the grains which make up the reservoir rock. The ability of the oil and gas to flow within the reservoir rock is dictated by its porosity and permeability. So conventional oil is associated with good porosity and permeability, and unconventional oil is associated with medium to low porosity and poor permeability. Also, if you're following along with the PowerPoint presentations, I'm going to start jumping around now from slide to slide, and the sequence might be a little bit out. I have been looking around to find a slide that really represents what we're trying to get across here with regards to porosity and permeability. Porosity is the space between the rocks, or grains, however you want to call it. High porosity means lots of space within the reservoir rock for the oil and gas to pool. So you can see that right here through the blue spaces. Permeability, though, I guess you could say is a measure of how well those pore spaces are connected to allow the flow of oil and gas. So on the right-hand side, here we have good pore space between the grains, and the pores are interconnected, which means you have good permeability, and the oil and gas is easily to flow within the reservoir. In the middle section here, you do have pores where the oil and gas can accumulate, but not a whole lot of permeability, so they're not interconnected. And this might be considered unconventional gas types. And here on the left-hand side is there's no pores and there's no permeability. This might be considered something like cap rock or salt that oil does not flow through. So just to make sure we're all on the same page, porosity is the void space between the grains and thus represents the rock's capacity to hold fluids, in this case hydrocarbons. So a highly porous reservoir rock can contain a large volume of oil and gas, but porosity alone is not sufficient. The fluids must be able to flow, meaning that the pores must be interconnected, and this characteristic is called permeability, and is the measurement of how the rock's ability to permit the flow of oil and gas. So when we're talking about permeability, we want to talk about unconventional gas, and unconventional gas is characterized by very low permeability. Ultra-high compact structures that prevent the migration of gas. And the two, well, we're going to talk about three actually, but two here are tight gas. So here in tight gas, the reservoir rock itself is very, very tight. The pores are there, but there's no permeability, or very little permeability. Shale gas is actually drilling down past what we would consider the reservoir rock and actually going into the source rock, which is compacted very, very tight over time and pressure, which we talked about earlier. And there they're trying to extract the gas directly from there. Conventional gas, reservoir rock, which we talked about earlier on, with lots of pores, lots of permeability, and everything flows naturally. I want to start with this slide by explaining a few areas here, just to make sure we're all on the same page. So this pink area right here, this is the source rock, and this is the geological layer in which all the oil and gas was generated originally. It was formed when all the organic rich sediments were deposited and sent to the bottom of the oceans and lakes. They were gradually covered by sediment, and pressure and temperature over time has chemically changed it into hydrocarbons. The hydrocarbons then migrate upward, they travel upward, and they are encapsulated or trapped in this brown section, which is referred to as the cap rock. The next part I want to talk about is this middle section, where it's kind of a tan color and turns a little bit lighter over here, and this is the reservoir rock. The source rock has been squeezed, and the oil and gas from there has migrated upward. Now over here on the lighter side, there is pores, so there's a place for the oil to collect, but it is very, very low permeability. This is a really compact structure, and because of that, you form tight gas over here, which we'll talk about in a second. On this section over here, where it's a little bit darker, this is what we consider a traditional well with lots of big pores and good permeability, which allows flow of the oil to transfer through here. And under natural pressure of the reservoir, when you drill your well, it naturally squeezes out and travels to the surface. Let's start talking about unconventional gas now and explain how that all works. So let's start with shale gas. Up here on the top, you have your rig. This drill string comes down, goes to the cap rock, goes down through the reservoir rock, and enters into the source rock. It turns horizontally here, and the reason for that is they want to increase the surface area for the drill string within the area. The source rock itself, we talked about earlier, was under a lot of pressure and temperature, and baits and all the oil and gas has now migrated out, but there is residual gas in the pores of the space here. But because it is so dense, there is very little or no permeability. So because of that, there's not a lot of travel, and that's why the string is in here horizontally to increase the surface area. Once down here, what they want to do is crack or fracture the source rock, which increases the permeability and allows flow for the gas to reach and then travel to the surface. The next type of unconventional gas is tight gas, and how that works is the source rock, the oil and gas has migrated up and has traveled through here and collects, but this particular section is ultra tight. The pores are very, very small, little or no connectivity, which means little or no permeability, and the gas does not want to naturally flow. So they put a rig up on top, the well comes down, and they turn horizontally to increase the surface area of the drill string. Same as when we talked about the shale gas. Now they crack or fracture the structure to increase the permeability and allow flow to start, and then that travels upward under natural pressure and comes up, and that is referred to as tight gas. And my third type is coal bed methane, and as the name suggests, it's drilling down into a coal bed. It's also sometimes referred to as coal seam gas, and we're going to show you a little picture of that, how that works. Now there's no oil associated with this, it's only gas, and what happens is the gas itself, it clings to the surface of the coal, and funnily enough, it is a great storage medium. You can actually get 2 to 3 more times gas per rock ton here than you would in a natural deposit. Unfortunately though, you have to put in a lot of water and chemicals so to fill up the spaces between to extract the gas for it to come out. This concludes section 2, folks, and if you could read chapter 3 in our textbook, that would be greatly appreciated. It'll give you a better appreciation and clarify a few points. Also, if you can find any cool little videos on YouTube to better explain these topics, that would be greatly appreciated if you send those along. Also, there's the weekly mini quiz, which I'd like you to complete. And aside from that, guys, have a good weekend. Thank you.